In our last example here, we've got independent variables, but they all have the same mean and the same variance. We want to find the mean and the variance of the average of those variables. So the average just means you add them up and divide by the number of variables you have. So it's 1 over n y1 up to 1 over n yn. And I wrote it that way to really suggest that that is a linear combination of the original random variables. So this is a linear function. And so we can use our theorem on how you calculate means and variances of linear combinations. So that's what I'm going to use. The expected value is the same as the mean, remember. The expected value of y bar, the mean and variance of the average. So the expected value of y bar is just the expected value of 1 over n y1 up to 1 over n yn. And I can distribute by linearity of expectation. That was the theorem that we had. So I can distribute and pull out those coefficients, 1 over n times e of y1 up to 1 over n times e of yn. And so that's 1 over n times mu up to 1 over n times mu. They all have the same mean, mu. And so if you add up n copies of 1 over n times mu, you just get a single copy of mu there. So that's my expected value of the average. The variance of the average, variance of y bar, again, is the variance of 1 over n y1 plus up to 1 over n yn. Variance is not linear. Expectation is linear. Variance is not linear. So there's a nastier theorem that tells you what to do with variance. And I gave you that theorem in one of the introductory slides. I said linear functions of random variables. So this is, the way this works is you pull out the coefficients, but you square them. So 1 over n squared times the variance of y1 up to 1 over n squared times the variance of yn. And then there's these cross terms. So there's this cross term, which is 2 times the sum as I is bigger than j of the coefficients, 1 over n times 1 over n times the covariance of yi with yj. So that looks pretty dangerous there, but let's remember that we were given that we have independent variables. So any y and j, if you take their covariance, since they're independent, this covariance will be 0 by independence. That's really nice. That means I can just focus on the first few terms here. 1 over n squared. The variance of y1 is sigma squared plus up to 1 over n squared times sigma squared. Now, let me write that a little more clearly. That's 1 over n squared in the denominator there. And so what I have is n terms here of 1 over n squared times sigma squared. And so that simplifies down to sigma squared over n. By the way, this is a very fundamental result in statistics. So this is something that you use very often as you get into statistics. The variance of the mean is equal to sigma squared divided by n. So this is kind of where it comes from. This is where the magic starts to happen, is right here with this example. So let me make sure that you understand every step here. I wanted to find the expected value of y bar. So remember that y bar, the average, can be written as a linear combination of these variables, and expectation is linear. That's what we learned in that theorem. So you can just separate it out into the expected values of y1 up to yn and just pull out the constants, and then each one of those e of y1s each one of those e of yi's is mu, because we were given that in the problem right there. And so we were adding up n copies of 1 over n times mu, so at the end we just get a whole mu. The variance is a little bit messier. The variance of a linear combination, again, you can split it up into all the separate variances, but when you pull out the coefficients, they get squared. So that's why we get 1 over n squared on each of these coefficients. And then there's this cross term, 2 times the sum of the coefficients. Those a little messy there, but that says 1 over n times 1 over n, and that's coming from these coefficients right here. And the covariance of yi times yj. The fortunate thing is that we have a theorem that says when two variables are independent, their covariance is 0. Converse of that is not true. Could be covariance 0 without independence, but if they are independent, their covariance is definitely 0, and we were given that they are independent here. So all of those cross terms drop out, and we're just left with n copies of 1 over n squared, and we're given that the variance of each individual variable is sigma squared. So n times 1 over n squared is just 1 over n, and then we still have that sigma squared. So the variance of the mean is sigma squared over n. Essentially, this means if you take the average of many things, it's not going to vary as much as individual members of the population will, because the variance sort of shrinks down as you take a larger and larger sample. So that's a very classic result in statistics, and now you know where it comes from. Now you know where this classic formula comes from. So that wraps up our lecture, kind of a big one today on correlation and covariance and linear functions of random variables. This is all part of the chapter on bivariate distribution functions and bivariate density functions. In fact, this wraps up our chapter on bivariate density functions and distribution functions. We'll come back later and talk about distributions of random variables, so we still have one more chapter to go. But in the meantime, it's nice to finish our chapter on bivariate density and distribution functions. This is all part of the probability lecture series here on Educator.com, and I am your host and guide. My name is Will Murray. Thanks for joining me today. Bye-bye now.